Okay, so today's idea is on transformations of parent functions. And when we say transformations, that falls into three main categories. We can translate something, which we can do in the vertical direction. So, what that's referring to is moving a graph up or down. So, moving something up or moving something down, that's a translation. Or in the horizontal direction, the equivalent would be left, left or right. When you have a translation, the shape of the graph remains the same. So if my original graph was a triangle, and that was my first original graph, and say it's on the XY axis right here, if I move that triangle up or down, I maintain the shape of that triangle. It's not perfect moved up or down there, but the shape remains the same. And same thing if I decide to move that shape left or right, it still remains that same exact shape. Okay, so that's vertical translations. Translations, they preserve the shape. Okay, so the shape does not change when you have a translation. Okay, reflections also preserve shape. Reflections can be in the vertical direction when you are reflecting something this way. Sometimes we call that over the x-axis, but the reflection does not always happen over the x-axis. But that's a common way that that's referred to. So, hypothetically speaking, if your graph is this and I reflect it over the x-axis, now your graph is this. And then we do the same thing when we go side to side reflections, and those are sometimes referred to as over the y-axis. And when we do that, so we have our smiley face here, and then we reflect it over the y-axis, and now it is here. You do have to use your imagination a little bit on my sketches here and imagine that I did preserve the shape nicely with those. So those ones are really straightforward to identify, and then usually everybody feels pretty successful with translations and reflections. Where things get a little bit more interesting is when it comes to stretches and compressions. So again, stretches and compressions can happen in the vertical direction, and they can either make things, so again, if we go back to our triangle, we can either stretch out that triangle or we can compress it. And then that would be in the vertical direction. So you'll notice like on all of those, the base size remained the same, but what changed was the height. And then when it comes to the horizontal direction, if we do the same kind of idea, we can stretch that triangle and it maybe looks like that, or maybe it gets compressed and it looks like that. So in these ones, what remained the same was the height, but what changed was the width. So these are the ones where we're going to see the shape changing. The shape is not preserved in a stretch or a compression. And we'll go through on the next couple of slides and talk about how do you see these in the equations and how do you know what is what. Okay, so those are the main transformations: translations, reflections, stretches, and compressions. The functions that I keep calling parent functions that we're going to be transforming are these ones here. And I'll zoom in on this in a second. But this document is as a PDF in your Unit 4 folder in the Day 1, Day 2 folder. So it's already completed. I just actually screenshotted it to make it aware for you. So one of our first parent functions is just a horizontal line. Then we have a linear equation. So y equals x, f of x equals x. We have the parabola, x squared. We have the cubic function, x cubed. We have the absolute value function, which looks similar to the parabola, but you see straight lines on each side. We have the square root function. We have the reciprocal function. We have an exponential function. And we have a logarithmic function. So really all we want you to be able to know is by sight, we want you to be able to know the equation for it. We're not going to focus in on the domain and the range of the equation or a table of values, but I want you guys to have a level of comfort. Whereas if I draw this graph and I say, what is that parent function? That you can make the connection to say, oh, I recognize that the V shape is the absolute value function. Or if I draw this one right here, I'll even put a little XY axis on this one. If I draw this one right here and I say, what is this one's parent function? That you're comfortable enough with that shape to know, okay, I remember that one. This one has to be a log function. So that's kind of our only goal with this. We're not going to, like I said, we're not going to focus in on domain or range. We're not going to focus in on the table of values. It's really just making the connection between equation and graph. And so that first homework quiz that is up there for you, the 4.0, is simply a matching quiz where I throw out a bunch of equations and you are going to drag the right picture to them. My challenge for you is when you do that 4.0 quiz, try it the first time. You have multiple attempts on it, okay? But try it the first time after you've looked at this sheet and just give it a try and see how many you know, okay? So just to be aware, just to check in, okay, I recognized 6 of the 9 of them, great. And then after that, if you want to try it again and see if you can improve your score, awesome. Otherwise, pull up that parent function guide and use that as a resource. Okay, but we want to get to this place where we're able to look at a picture and name the equation that goes with it. And that's the main goal for this. So that's the 4.0. So that's one of the things that you're going to work on for over the next 2 days, either today or tomorrow. And it's like I said, it's just a matching quiz where one column has equations, the other column has pictures, and you're going to drag and drop to make it happen. Okay, so now let's talk about those translations and how they show up in the equations. Okay, so I'm going to go through all of the vertical transformations first, and then I will switch over and do the horizontal transformations second. And as always, like I said, this video is going to be available for you, but so will the completed notes to refer back to. Okay. So there's going to be 3 slides for each vertical and horizontal, because we have, like I said on the first slide, we have translations, we have reflections, and we have stretches and compressions. So there's going to be 3 slides for vertical going through each of those and 3 slides for horizontal going through each of those. Okay, and at the top of each of the vertical slides, you're going to see this same line here. Vertical transformations happen outside of the function. And I'm going to show you a couple of examples of that in a second to help outside click. And my reminder for them is that they do what you think they should do. They do what you think they should do. Okay, so if you know that it's outside, then they do what you think they should do. So here's my example to kind of help that all make sense, okay? So here's my plus or minus c happening after the function. And here's my parent function, okay? Y equals x squared is the parent function that I'm going to use as the example here. There is nothing going on with the x squared, it's just y equals x squared, okay? There's not plus anything or times anything, it's just y equals x squared, plain old naked function there. Now over here in this graph, what you see here is you see y equals x squared plus 4. So one thing I want you to recognize when you see an equation like that is that that plus 4, like I said, it happens outside the function. And what do I mean by that? I mean, it's not getting squared, right? That plus 4 is not part of the squared. It's after it, okay? It could also be before it, but in this case, it's after it. So we call that outside of the parent function. And what do we see in the graph? we see that this same exact shape right here has been shifted up 4 spaces. So what did that +4 do? It moved the graph up 4. So that's what I mean when I say it does what you think it should. When you see +4, plus translates in the direction of up. So that whole graph just shifted up. Likewise over here with my third graph on the right, you see a similar thing, right? You see -7. This -7 is happening outside of the squared. It's not inside. It's not getting squared itself. So if I say to myself, okay, I know it's vertical and it has to do what I think it's going to do, then -7, as you see in this graph, moves the graph down 7 spaces. So like, for example, if you saw y equals the square root of x minus 6, and I said, what happened to that graph? What transformations happened? What I want you to be able to recognize is that number 1, the parent function is the square root of x. That -6 is happening not underneath the square root, but after the square root, outside of the square root. So that tells me vertical, and it does what I think it should do. So -6 would move that graph down 6 spaces. Let's do one more. Let's say we had y equals the log of, I don't want to do log. Let's do 2 to the x and then plus 10. So in this case, all right, Grace, the parent function is 2 to the x. And the thing that's happening outside of it, that's not getting raised to a power, is plus 10. So I think that should move it up 10. And I would see that in the graph as well. So translations are really straightforward when it comes to the vertical direction. Plus is up, down is minus. So if you want to summarize that, when you have your function plus a number, that is going to move up by whatever that amount is. And if you have your function minus a number, then that is going to move down by whatever number you happen to be asking. So again, this right here, this is demonstrating 2 vertical translations and showing you how up is going to appear and how down is going to appear. So kind of as a little summary for you right there. Those are my vertical translations. So now I'm going to go through and I'm going to do reflections, vertical reflections. So when it flips over the x-axis, and I turn my smiley face into a frowning face. Oh, maybe I'm not doing reflections next. I'm going to do reflections next. Here we go. So reflections, you'll notice a theme here. It is also happening on the outside of the function. And the thing that makes a graph reflect is a negative sign. So when we see a negative sign outside of the function, what action that takes with the graph itself is it takes, as we talked about in Unit 2, it takes an upward facing parabola and turns it into a downward facing parabola. So an example of that in a couple of different functions, let's make it negative x cubed. The parent is x cubed. The negative is going to cause a reflection, oops, gotta spell that correctly, over is with a V, over the x-axis. Some people like to call that just a vertical reflection, and I'm totally fine with that as well, if that makes more sense to you. Here's another example of a vertical reflection. Let's do the negative log of x. So the parent function would be the log of x, and the negative would, again, you can either call it a reflection over x, or you can call it a vertical reflection. So when you see that negative on the outside, not inside the function, that causes it to be a reflection in the up and down direction over the x-axis. Okay, so put a summary on the bottom of every slide. So negative f of x is going to cause a reflection over the x-axis, or if you want to call that a vertical reflection, that syncs better with some people, that's another way to describe it. So we got that one. Now we'll go to translations or compressions and stretches. So again, with vertical, the theme for vertical is that whole outside, right? So when it happens outside the function, you see that shows up right here with a number being multiplied to the function itself. So the way this one is looking like is a number is multiplied to the function. So you can see I have two examples. I have 5x squared and I have 1/2 x squared. And so we're taking our original parent function. In this case, it's the blue one. The blue one is x squared in both of these. And when I do 5x squared, what's happening there is what we're going to call a stretch. And whenever we name any kind of translation, if it doesn't have a direction like left, right, up, down, we need to give it a direction as in vertical or horizontal. So when I say it's a stretch, I'm going to call this one a vertical stretch. And when you name a stretch, you have to say by how much. And so this one's by 5. So what you can see is you took that parabola and you pulled it up so that it's 5 times as skinny. So it's like it was here, like I'm doing my goalpost arms, and now I'm going to stretch it so that it's 5 times as skinny. So now my arms are just getting a lot tighter like that. So that's a vertical stretch by 5. Remember, vertical always does what I think it should do. So once I know that it's vertical because it's outside the function, and I think of a multiplying by 5, what's that going to do? Well, that's going to make something bigger. It's going to stretch it out. So it is a stretch by 5. On the other hand, in this picture, you don't see that the parabola got more stretched out. What happened to this parabola is it got smushed, it got compressed. So again, my goalpost arms were here, and now I'm going to make them half as wide, and now I'm here with a wider goalpost. So that 1/2 took the height of this and it pushed it down so it's half as big. So I would call this one out as a vertical compression. And how much did it compress by? It compressed by 1/2. Oftentimes we feel a little lazy when we're doing this kind of stuff, and so we find ourselves just abbreviating this, and I might just write VS for vertical stretch by 5, or over here, VC by 1/2. So one thing that I hope you're kind of wondering is like, when does it switch from stretch to compression? Like what number? Well, anything bigger than 1 is going to be a stretch. So let's summarize here. When you multiply your function by a number, and if that number is bigger than 1, that is going to lead to a vertical stretch by whatever you multiplied it by. And again, I just said I oftentimes abbreviate that. So I'm going to abbreviate that for us. We oftentimes would just call it this, a vertical stretch by A. When we multiply by a number, and that number is between 0 and 1, so anything from 0 up to 0.99999, that's going to cause the graph to be vertically compressed. So this one will show up as a vertical compression, and it'll still be by A, and we abbreviate that of VC by A. Okay. So that has covered vertical. Like I said, everything that happens in the vertical direction, the things that the vertical direction have in common is they happen outside the function and they are as is. So when you see +2, it's going to go up 2. When you see -6, it's going to go down 6. There's no mind switches to any of that, which is kind of prepping you to the horizontal side of things where you are going to see some mind switches. So now I'm going to go through the horizontal ones. I'll go through them in the same order so that we can see the difference between, she keeps saying outside, but what does she really mean by outside versus inside of a function? And what does she really mean by as is versus something else? So I'm going to show you that part now. So now we've got horizontal transformations. And this line's going to show up on top of all my horizontal slides here. So the connection we're going to make for horizontal is horizontals always happen outside the function. I didn't change that. My apologies. That should say inside. So let me fix that real quick. They always happen inside the function. This is the fault of all my copying and pasting to create my slides. You don't catch things like this. They happen inside the function. And then you'll notice also I wrote, they do the opposite of what you think. Okay, so here are my 3 graphs. The red one on the left, the leftmost one, this one right here, that's the parent function y equals x squared. You're all familiar with a parabola. Okay, it's opening up. Now on the center graph, I have y equals x plus 4 squared. So that's what I mean by inside. Can you see how this plus 4 right here, it's inside the parentheses of the parent function's operation of squared. The thing that made this shape was the squared. So that's what I mean when I say inside the function. Whatever makes the parent function itself, whether it's a square root bar or an absolute value bar or a cube power, whatever that identifying trait is that makes something its own parent function, if you put an operation inside of that so that that operation is happening to whatever you've added, that makes it inside. So that plus 4 is inside of the squared. It's getting squared. And then what I mean by opposite is my brain tells me that if I add 4 to something, it should go this way. But look at what happened on the graph. The blue graph of x plus 4 squared did not go right. It did the opposite of what my common sense tells me, and it went left. So when this plus 4 happens on the inside, we ended up with left 4, not right 4. And the same thing is going on over here. This minus 7, because of these parentheses, that minus 7 is getting squared. That minus 7 is inside of the squaring function. And so I have to switch my mind. Minus is not going to be to the left. Minus actually turned out to be RIGHT to the right 7. So I want to show you a couple of different examples of those, and we'll look at what are the parent functions and what is the transformation. So let's say we did, here's an example using a different equation. Here's another one. And let's do one more. How about that one? So I was very conscious not to name those as I wrote those because I didn't want to give away what the parent functions were by calling them by site. So my parent function here, the identifying feature is the square root of x. You have class again at 1:30, so you have an hour to play. Yeah.
I want to play for 10 minutes.
Okay, go downstairs and see if you can get it out, and I'll be down in a minute. Let's do it downstairs on the table. Okay? Okay. My parent function on this third one is absolute value of x. So those are 3 different examples of parent functions and what it looks like to put a translation inside of it. So +6, if I switch my brain, that's left. +5, that's left. -3, that one's going to be right. So those are 3 different choices there. So again, in summary, if we see the plus happening inside, that is going to show up as left by whatever that amount is. If we see a minus showing up inside, that one's going to translate to right. So we have inside. A couple examples of inside we did up here. Okay, so that's our summary for horizontal translations. All right, now let's do the reflections. Okay, so you can see in my picture, I have the square root function graphed right here. There's the square root of x. And when the negative goes underneath the square root or inside the square root, how that shows up for us is just like the vertical one. We can either call it a horizontal reflection, or we can name this one as a y-axis reflection, whatever one makes more sense to you. So I'll write out a couple of different equations that would be an example of an inside. Let's say we could have y equals -x squared. That's on the inside. We could have y equals 1 over -x. We could have y equals the absolute value of -x. That's a couple of examples of insides. So let's summarize that. When the negative is here, that is going to show up for us as a horizontal reflection, or if you would rather call it a y-axis reflection. Want to say hi to everybody, Grace? No? Okay. All right. All right, so one more thing to go through, the horizontal stretches and compressions. So we're still sticking to the theme of outside and doing the opposite. We are still back to what we did with the stretches and compressions vertically in terms of now we're talking about multiplying by something. So now in this case, we are multiplying inside. So you can see, like, for example, right here, that 2 is inside the parentheses, so that 2 is getting squared. This 1/5 inside the parentheses, so the 1/5 is getting squared. And to speak to the opposite portion, now what we're seeing happening is while this 2, let me zoom in on it. While this 2, my brain tells me that I think that should be getting wider, like twice as wide. The 2x squared right here is actually skinnier than the x squared because this time here's my x squared and this squeezes it in. It compresses it. So what this one shows up as is a horizontal compression. And now here's where the opposite part comes in. It's a reciprocal here. So when we name this 2 becomes 1/2 because the opposite in terms of this is the reciprocal. So over here, this one actually got wider. Here is your 1/5 x squared, and here is your x squared. So what happened in this one is this one was a horizontal stretch by the reciprocal of 1/5 becomes 5/1. You can go downstairs now. I will be downstairs in 15 minutes.
How much would that come to?
Count to 15, 60 times. So as a summary, here are our horizontal stretches and compressions. When the number is bigger than 1, like the 2x squared example, this gets described as a horizontal compression by 1 over a, the reciprocal. Okay, so whatever this is, this right here is the reciprocal. When that a value is between 0 and 1, so you see that fraction there, that comes out as a horizontal
What if I,
stretch.
how much do I have to count up?
You have to count to 60 15 times. Go do it in your bedroom,
I'll
please.
just count to 60 in quiet.
Perfect. So again, this is flipped over. So like, for example, if we said 2/3 x cubed and said describe that,
Which number?
this is horizontal
16?
60 because it's on the inside, right? The 2/3 is on the inside. And when I say by how much, I'm going to reciprocal the 2/3. I'm going to flip it to be 3/2. So it's a stretch by 3/2. Here's another example. Let's see. Yep. So this 3 is great, is inside. I'm going to reciprocal it. So it's going to be by 1/3. So we have a horizontal compression by 1/3. So what our goal is going to look like on today's assignments is you're going to see a combination of things like this. So you're going to see at most sorry about that, little parenting moment. So we're going to try to pull out both of the two transformations. So the trick is, number one, think about what you see that makes your transformed function differ from your parent function. So for example, here, my parent function is x cubed. So what in that black circle do I see that is different than x cubed? Well, I see a negative sign. So we got to deal with that. That's causing something to happen in my graph. And I see a 3. And so both of those two things are affecting how the shape of this graph is going to come out. We want to be able to identify how they affect it. So then the thing we want to be able to do is like, okay, let's look at each one of those individually. Let's take that negative sign. Is that negative sign inside or outside of the cube? Like, is the negative getting cubed? Well, yeah, because there's parentheses around it. So this negative is inside. So if we go back through our examples and we look where we put negatives inside, that would be our example here. The negative is inside the parentheses. So that will come out as a horizontal reflection or a y-axis reflection. So we want to be able to recognize that this will show up, and you can write it either way, as a y-axis reflection or a horizontal reflection. And then we do the same thing with the 3. The 3 is also inside the parentheses. It's getting cubed. So we go back and we find out, where did we talk about multiplying on the inside? That would be right here. So that 3 is inside. It's bigger than 1. So that means that this is going to show up as a horizontal compression by 1 over 3. So that's what I'm going to write for this one. It's a horizontal compression by 1/3. So it all comes down to, first things first, being able to see what's the parent function. And the pieces that are different than the parent function, in this case would be, we've got another negative sign, and we've got a +2. and whether or not those things are happening inside or outside, right? So that +2 is happening to the x. This is a little bit trickier. The parent function being 1 over x. So it's happening right there to that x. So that's an inside. And when it is an inside with a plus sign, if we go back to that, that was my 4th slide here, that translates as left by that, whatever amount that is. So this is going to be left 2. And then there's that negative sign, which is not happening to the x itself. It's happening in front of the entire parent function. So that one would be on the outside. So if we slide back to outside and negative, that shows up as a reflection over the x-axis or a vertical reflection, depending on what we like to call it better. So this would be the 2 transformation would be x-axis reflection and left 3. I'll do one more. Parent function here, square root of x. The 2 things that are happening to the square root of x are the 2/5. And then over here, the +6. The +6 is not underneath the square root, so it is outside of the square root. So that's going to show up as up 6. The 2/5, that is under the square root, so opposite of what I think. I'm going to reciprocal it. I know that when it's inside, it's horizontal, and this one's going to show up as a horizontal stretch by 5/2. So that's what your homework looks like for tonight. Let me pull it up for a second. It has, or tonight or tomorrow, whenever you want to do it. It has, how many is it? 8? Yeah, has 8 different equations on it where you're going to go through and you're going to look at that first equation and you're going to say, what's the parent function there? Well, the parent function to this one is x squared. Then you're going to tell me, what does that -1 do to the graph of x squared? How does that show up? So whether you've got it memorized or you're just referring constantly back to your notes, either one is totally fine. But our parent function is x squared. This is happening outside of the x squared because it's not getting squared itself. So that's going to show up as down 1. Like I said, there's at most, let's see, I'll go through and tell you how many are on each one so that you know how many that you're looking for description wise. That one's got 2. This one has 1, 2, 3, 4. This one has 1, 2, 3, 1, 2, 3, 4. Just quicker to write 4. This one has 1, 2. This one has 2. This one has 2, and this one has 2. So on each one of those graphs, those numbers in circles, that represents how many transformations you are looking to describe. So again, identify the parent function, step 1. Number 2, look for the things that make your equation different than the parent function. And then how do those pieces change the shape of the graph? And that's the goal for today. And if this is feeling like a lot, remember, I'm going to post these completed notes, but I'm also going to post this video so you can watch it again if you want, including the lovely interruptions by my dear Grace. And we're spending the whole week on this and even some of the next week when we come back. So there'll be plenty of time to help this sink in and help you guys feel successful with this. And I am sorry I talked so long, but just think you don't have to hear from me at all tomorrow. So do me a favor and turn your camera off and wave goodbye and then leave if you're ready, or stay if you have questions. But I have hardly seen any faces today and I miss your faces. So have a fabulous day. Thank you. You guys are the best. And I will see you Wednesday, or stay if you want to ask questions. I am totally here. Bye, friends. You're the best. This hour is awesome. No, that quiz is not supposed to be 1 attempt. Let me go fix that real quick. Thank you for catching that on me. And I'm not on the screen looking, so if anyone else is typing something right now, I'll be right back to that in a second. It should be, I went with 5. Let's go even more than that. Let's go 20. Okay, that should be fixed. Thanks to you for that, Alexandra. Got that fixed.
Bye.
Bye. Have a good one.